Okay, this is a continuation because I accidentally stopped the video. Alright, so now we are looking at main in front of you right now. We have two instances of two objects that we've created. Object number 1, and we're going to set the age to 10. Object number 2, set the age at 15. And we've created the two objects here. I'm purposely kind of going through this on the little slow side just to give you, because some people I know are a little bit lost at this point. And so slow it down a little bit, just kind of show you piece by piece how the pieces are coming together here, just in case you do fall into that category. And then we're using a printf again. There's better ways of doing that. But what are we printing out here? We're actually running a method call in Objective-C and running it to a C function, which is kind of interesting. And the method that we're calling is on object2 space grow sum. So just for those people who are lost and we're just trying to make things a little bit easier here, we're looking at an Objective-C method call inside of a C function call. For those of you who have a C background. So some people find this example helpful because it kind of puts the pieces together in terms of what it is we're doing with function calls and method calls. So if we run it, it should hopefully run. And some people at this point wonder, well, I put a teacher object in there and I didn't make any instances of it, so don't have to, didn't do anything with it. But you might also notice here at the bottom, you see the output, so it ran here on the bottom. I set age is equal to something 10, age is equal to 15, grow results makes 150. Here's our grow results after we've run this grow sum method. You might notice in main we've included employee.h. When you're going to make an instance of the object inside of it, you're going to include it. So as an example, if I was going to include, let's say, this teacher that I made, I can say import teacher. And then inside the code, I can make another object to allocate a teacher, but just by using the same thing. And you're wondering, well, why don't I really have anything in teacher? Well, teacher is an employee and a person, so I have all of that stuff in there. So I can say, object 3 is equal to, let's just cut and paste here. And we'll change this one, make it a teacher. And I can see I can kind of grow this example a little bit more because I can also run a set age. So I can go here and I can go, actually, you know what, we'll just change the code. I'll just make 2 to 3. And now I can set the age. And over here, print out 3. Yes?
Import person, is it because it's directly
inside of employee? Yeah. In fact, at this point, don't even have to import employee. It's inside of a person. And what is this message going to tell me? Unused variable 2. Yes, I know it's unused. Let's just comment it out. And then now if I run it, I see the teacher is an employee. And the teacher is also a student. Or excuse me, the teacher is also a person. So even though I didn't add anything to teacher, teacher was completely blank, 100%. In fact, I think I added some fake ID or something in there, some teacher ID that I didn't really use it for anything. But you can see I'm using this teacher exactly like an employee at this point. I just changed it and made it object number 3 and printed out 3 here. Questions on the simple version? So if you want to practice with it, one of the things you can do is make your own teacher object, add more stuff to it, advanced, create some more methods to it, run the methods. It's going to run just like the person, just like the employee. The trick here is that, I'm using a teacher now, and the teacher is both an employee and a person, and I'm running the previous objects. Why do you want to do that? Well, you want to specialize it. You want to make it so that it has something else, and now it has a TID in it, if I were going to use it for something, without having to go back and redefine employee. Because I might have employees that are janitors, employees that are teachers, employees that are TAs or something, different types of employees. So. And then I can specialize each one of them, and then they would all have their own separate identity that's associated with them. All right, let's take a look at the second example that is part of that same download. And here it is, in part of code 3, by the way. So that was number 1. So let's go to number 2. And number 2, is this the one that has the, nope, this is square and rectangle. So this one's got no fishy C code in it, no fishy half synthesized and half regular. This is a upgraded example. So we have a square, and we can see that a square is let's take a look at the .h file. A square is coming from rectangle, so let's take a look at rectangle first. So rectangle is the base class. This comes from NSObject. And we're using property and synthesize in here. And we have yet another example, just slightly different implementation. We have a height and a width, and then we have an initializer, lo and behold. So, yes?
Very short, I announced a little mistake is like in this.
I'm so sorry for the interruption. Alright, so now we have a upgraded, I shouldn't say it's a more advanced inheritance example now with an initializer here. So we're going to have a rectangle that gets initialized, and the rectangle is going to have a width and a height that's associated with it. So this is a very classic looking initializer starting out with the word init, which is how we tell it's an initializer. Then we have a set width, and then we have a print method that we're going to do. And the set width is going to set the height and the width of the rectangle. And in the implementation of this, in our initializer, we're going to use this kind of format again. We're going to say self is equal to super init, which means make a super. And then if self returns, then self set width to the w, set height to this. So we're going to set the width and set the height using the set width and set height for self. Which is interesting because we're doing here self, height, and width. And then return self. And then we have this method here that's being called inside of it. And this method here is the set the height and the width. So inside of the initializer, we're running one of the members. One of the member functions. We're sending a message to itself, and the message is coming from inside of its implementation. So it basically shows you that you can call methods inside of the initializer and not have to rewrite the code. So what is an initializer normally doing? It's initializing. It's running the sets version of it. So you can run the sets inside an initializer instead of, well, 2 lines of code instead of 1 line. So you saved yourself a line of code. And the print's just going to print it out. So it's going to, again, using the printf, for lack of better examples here. So let's see, take a look at the square. The square is a rectangle. And we have a new one. We have initialize with size, S, for the square. So we're running a different initializer on this, and we're going to set the size to S. And we have an integer size as well. It's going to return the size. Because this one here is using the property and the synthesize, but we overloaded the set width with our own set width. So here's the thing. So if you use property and synthesize, you can rely upon what gets property and synthesized. If you write your own method, it will replace the one that's automatically given to you. The one that automatically given to you is going to do an assignment or a retrieval. Same behavior. So there's no need really to write it again because we property and synthesized it. But it's showing you that you can, actually. So in the square, we're not synthesizing at all. We're not using a property. In fact, we don't have actually anything in here. We just have this S for the size. In fact, we don't even have any data in here. So we're just setting the width to size. I'm going to set the width. And so in the square, in the M implementation, we're going to run a set size to S. And set size is going to set the site width and the height. And we're not actually running anything from, and this is kind of showing you, we're sort of skipping, although a square is a rectangle, we're skipping the rectangle. We're not running an initializer, we're running, instead we're going to run the initializer of init and go directly to self from init to super. So self is going to be equal to super init if self doesn't come back, or if it comes back correctly, self set size to S. And so we're going to run the set size, and set size is going to set the size, height, and the width both. Because a square has the same height and the width, it doesn't necessarily have 2 different numbers. Then we only need to take 1. So it kind of just shows you a little bit more flexibility that you can do that. Although we are inheriting, this example isn't really reusing anything. It's redefining its definite properties of the sides. And so in main, we can kind of see out here, and this is another kind of way of looking at this project as well. We have the classes outside of the main in terms of the organization of this project. and we put the main inside. You don't have to do it this way. You can put it all inside of the same example if you wanted to. Same folder, I should say, if you wanted to. So main is going to do exactly what you think it's going to do. Here we have a square and a rectangle that we're going to import in. And in the importation here, we're going to say rectangle, rec, allocate a rectangle, init with size 10, height 20, size, we're going to call it SQ, excuse me, square, SQ, square allocate, and initialize with a size 15 because we're only taking on an S with this particular, so this initializer is only taking on one value. This init with width and height is taking on the two values. Let me get rid of this sidebar to make it bigger. There we go. And so now we are going to print out rec print, square print, rec print, and we're saying, where does this print come from? Well, we have print. Print is in here. Print, that's implemented in here. Print. And then so in here, we don't have a print, we don't need a print. So we're using the print that came out of the rectangle. Because what rectangle print's going to do is going to print out the height and the width. If we go down to the implementation of print, we see there's a width and a height. But we set the width and the height inside of square. Here, because we set the height and the width to S. So we're still using the same members as we were using before, but a square does have a height and a width. It's set the same thing as set to S, and then S is going to print out. Excuse me, size, if we wanted to do size, is going to print out the width. It only needs to print out one of them because the height and the width are the same. So in the main, we have this interesting little thing here. We're just going to print out rectangle, print out square, square, set the width, and we can set the width of a square after the change, and so we say set width of a square. Look in square, and we go, there's set size, but there's no set width, but there's a set width over here. And the set width over here is setting the height and the width. So, excuse me, set width is, where's it here, set width, with height. So, it's going to set them both to the same thing because they're the square. Anyway, hopefully it's kind of a clear example for you. If you run it, it's just going to print out some stuff on the bottom of the screen. It's going to say a rectangle. Here's a rectangle with a height and width, a square with a height and width, and a square after the change. The width is 20, the height is 15. So you're looking at the ability to reuse and then also treat the object as a separate object and run its own methods on it, and then reuse anything that might be existing before that. So that's why we use inheritance. We have another example here called protocols. Take a look at protocols here, which is kind of a slightly different concept. Not really inheritance, but along the same concept. So we have a fraction, and then we have complex that's in here, and then we have this thing here. This is the protocol. It's called printing. It's not part of fraction and it's not part of complex. It's a separate class. And this is when we get to actually kind of look at it and go, oh, what in the world is this thing here? And we just have a .h file that comes out of it. So in Java they call this an interface. And C++, what do they call this? What do they call it? An interface? Virtual method. They call this an abstract class or virtual method. It's a sets of, well, protocol stands for rule. It sets a contract. If you include the protocol, extend the protocol, you have to implement the methods, which means you're going to have this in this class. So what we're doing, instead of now taking one class and building it from another class, we're taking a bunch of classes and making them abide by the same rules. And if they implement, in Java we extend and then we implement, extend this class and implement another class, we do it together. It's the same concept here, but we don't have to extend and implement. Instead, we just include the protocol, use the protocol. Let me show you how the protocol works. I have an example. We'll do it next time, actually, that we'll bring up and actually show you, because I want to set people's devices up today. So we have an example here that will create a protocol for you. There's also another concept that's associated with this as well, but I want to kind of mention this in terms of the concept. So we create a protocol option, not a class, creates just the .h, so there's no corresponding .m, and it doesn't get compiled as a separate unit, it gets compiled along with the other ones. So we import here the regular import, and we define the protocol this way. So what you're looking at is the body of the printing.h protocol. And so we're calling it protocol printing. And if we come up here and we go File, New, File, actually we'll just show you there's a protocol option. There's also a category option. I'm going to talk about that next time when we do the protocol and the category implementation, because building the code is a little bit more than an hour or so. So I want to make sure we have time for the device stuff today. But if we select here Objective-C protocol as an option, we can just create one and call it test as an example. Add it to the project. You'll see we're going to get the same thing as before. Here's another one. So that's how I got this one here that says printing on it. And you see the main body just says this here, and it's going to test is extending NS object, and this protocol here is using a slightly different, in fact we don't have to include NS object on that, we can just leave that out. This is the older way of doing it. The newer format, the newer template extends NS object out of there. But anyway, so what do we have in here? We have printing. And so, and actually I'm sorry, we define the protocol here. We have the interface to the printing protocol here, so we're still extending it. So the interface, not to be confused with an interface file, defines a single method, printing, or print. So we're going to implement the protocol two ways, one with the fraction and another with the complex number. So let's see how this works. In the fraction, we use this syntax here to include, so instead of saying implements this interface, we're calling the interface a protocol, and so now we're saying, same as before, if we leave this out, no problem at all. It's just not going to be a contract that says we're going to have printing in here. So implements the printing protocol, and then you might notice, well, we don't have printing in here. Well, it's not really part of, it's not part of this particular method, this particular class implementation is part of the protocol. But in here, in fraction.m, we have print down here on the bottom. So in the fraction.h, we don't have print. We have two properties. We have a numerator and a denominator because it's a fraction. And then we have an initialize with numerator and denominator. So we can create a new fraction. And then this one's going to implement the printing protocol. So the opening and closing this opening and closing arrows is a must. That's how we know it's a protocol, actually. Otherwise, we leave it out. It looks like a regular old class. And then we have to put this in here as well. We have to include the import of the printing.h. So now in the fraction.m, we just put print in here. If we leave print out, we're going to get a message, an error message, that says we didn't implement it. Because you have to implement everything that's in the protocol, just like an interface. It has to be implemented. So let's see, numerator and denominator. This is an interesting thing too. This underscore is a rename, which is kind of interesting because some people like to use it, some people don't. I don't actually prefer using it. In fact, I'll just synthesize numerator. But to say that numerator equals numerator with an underscore in front of it, when you're using it, you're using the setter, the getter name for the numerator. It's numerator instead of numerator. You can actually call this anything you want. For a long time, the projects were actually putting this in for you automatically. Now people are leaving it out. So this is a very old style, actually. It's just one way of renaming the variable, the data member inside of the implementation instead of using it as what it's supposed to be, which most people would leave it out. Anyway, so we have self-numerator, self-denominator, and so we have our fraction initializer, initializing with numerator, denominator. Same code as before. So after you've looked, this is like maybe the third time we've seen the same format. This is the format I use. You're going to put it all together in one line if you want to, and say if it's not equal to, if it doesn't come back, make it equal to nil, else do something else with it. But here we're going to go if self set the numerator and the denominator, return it. Now we're going to have this one here. It's going to print out numerator and denominator. So if we run the print on complex, take a look at this. We have the property and synthesize name as before, real and imaginary. And then we're going to initialize it with a double and a double. And so we have the real and the imaginary part of the number. And then in the .m file, our print is going to print out the real and the imaginary. So if we run print on an instance of a complex number and we run print on the instance of the fraction, we're going to get different implementations of it. The method name is going to be the same, but we're going to get a printing of a real number versus a fraction, or excuse me, a complex versus a fraction. So it's come out at. So if we take a look at main, and just to finish this up, the initializer should look vaguely familiar at this point. It's the same syntax that we're seeing for all of the initializers. So the initializers that take on values on the command line are just going to add them in. So if it, yes?
So the benefit of protocols is that it provides you the flexibility of implementing those methods as per your class needs.
If the class is abiding by the protocol, all classes that are abiding by it all have this print method in it.
Yeah.
So it doesn't matter what instance we're creating, we all have the print. Makes it consistent, makes it all the same, and it's going to pick the method that's being implemented per the implementation.
It gives a kind of flexibility to the user
Correct.
to implement print as they need for that particular class.
It keeps the integrity. It's like why we use abstract. If we have a shape, let me use a shape example because this makes more sense. If we have a base shape and we want to implement this concept of an area, well, what's the area of a shape? Well, it depends on what kind of shape you're talking about, which is the same thing with the print. What's the print? How do you print out a complex number versus a fraction? So don't implement it. So in other languages like C++, we call it virtual. And then we call it, sort of anything that's virtual is an abstract, which means it's not implemented. Well, there's pure, actually C++ is different because there's pure virtual, and then there's just virtual. So it's either implemented or it's not, or partly implemented. Long story short, we're delaying the implementation until later. So in Objective-C, they call it a protocol, which means if the object is supposed to act a certain way, if we were a shape, naturally we'd want the area. If I were doing a shape here, which I might actually do, I might actually have the example already, and then we have an area of a rectangle and an area of a circle, and they both abided by the same protocol, so they both had area as a method in there. I'd implement, and if I didn't implement it, I'd have a problem because it's not going to compile for me. What is that? It makes sure that you have the integrity of that object created, so there's no way that the user in main is going to write print the area and there's no area implementation, so that it's not going to compile unless it is implemented. Well, do you really have to implement it? Not really. You can leave it blank. Just include the method and then later implement it and then later implement it, which is kind of the same concept of leaving it abstract. So if you had like different components that were all coming together in terms of the inheritance, you could delay that protocol implementation until further down the road. Because the same thing as in other languages, you can overload and override. So if you're overloading, you're just using a different signature in terms of the method body, number of parameters, the order of the parameters, and it's a completely different method. If you just reinvent it, just create it again, you can have different print methods actually in each of your inherited classes. This is not going to use inheritance. Fraction and complex aren't inheriting from each other. They're all at the same level. But if it was included in inheritance, it would work the same way. You'd have to include it. Or actually, you don't have to include it if it's already implemented in the complex. If I was, I'd leave it blank and then rewrite it. So let's see. That was a good question, actually. In main, what have I got here? I'm going to use ID in here too. So I got a fraction, and I've got an instance of the fraction is called frac, and I've got a complex number, an instance of it's called complex. Now, both of these guys are abiding by the same protocol. So I'm going to make an ID printable object. Make the object printable. abide by the protocol. So first define the objects which implement the interface, and then the variables ID that implements the interface as well, also implements the interface. And the reason this object is of the type ID is so that we can implement multiple interfaces. So the ID can reference both a complex number and a fraction simultaneously, or one at a time. So it's reserved object, obviously we know that, meaning object, so ID is just generic for object, and then we can switch back and forth. If all three of them abide by printable, or printing I should say, which is the name of the protocol, then they all have the print method. And so if the ID is pointing to a complex number, it should print out the complex. And if it's pointing to the fraction, it should print out the fraction print. So let's see what happens. So printable, which is the name of our ID. So what we've just basically did is make liked objects. IDs of liked kind, they all have printable. And because they all have printable, they all have print. So we took two different objects and we put them on the same level, made them the same, gave them the same method. Now we're going to use them with ID, which is a common way of doing it actually, so that we can just print it out. So printable is going to be equal to fraction, and then print out the fraction is, and then printable print. Now printable is going to be equal to the complex, and now print out printable print. And we're going to get this printable print from the fraction, and then this print is going to come from the complex number. So if we print it out, if we run it out, tongue twister day. We have a fraction is 3/10, and a complex number is 5 point something or other plus 15 point something or other. And because this is an ID actually, so this one, because it's an ID and we're abiding by the protocol, it's all the same. It includes all of the same methods. And this is also demonstrating dynamic behavior, by the way, because it's dynamically figuring out from which instance this reference is pointing to, what print method to print out. Because there's two separate objects in memory. The ID is just the reference to the object. The ID is called printable. So if printable is pointing to the fraction or the complex, printable knows as an ID, it knows about the print method. If we start running one of those other methods, I'm not going to have the same results. Because it's not going to know. ID is a generic ID reference. All it knows about is the printable protocol. So it's not going to know about set width or set height, or I don't know what else we have in here actually. I don't think we have anything too complex. No, we just have initializers in here. We don't really have anything. But if you wanted to make this not work, you can add some other methods to it, have the ID point to it, and call one of those other methods. Not going to know about it. It knows about print because ID is also following print. So because of this wording here to include the protocol, it knows about the print method, which means that print method's going to work down here. It's not going to work with any of the other methods that are inside of any of these objects. So people create protocols to make all like objects, treat all the objects the same way. That's another reason why I use interfaces. So sometimes interfaces are used to keep track of, to make sure you can, preserve the integrity of the base classes, and you're going to implement everything that's supposed to be part of that object in terms of and keep it going throughout the hierarchy. Another reason is to make them all like kinds. It's not an is-a relationship, which is different. It's more they belong to the same group, and if they belong to the same group, they're all following the same rules, and following the same rules, they all have print method, which means you can run print on all of them. So why do you want to do that? Well, let's say you have a big old application for HR, and you have a person, an employee, and you have teachers, and you have janitors, and you have staff, and we built that up. Add a protocol to that. Put in the protocol, check ID, and on any one of the objects, regardless of what the object was, you could run the check ID on it, and it would tell you who the object was. It would return the object type. So some people use interfaces for objects, protocols and interfaces are pretty much being used the same way in this context, so that you can ask the object what it is, and it can return its ID. So it knows like a name or an ID that's associated with the object, and you have all these instances of all these objects out there, and you have them being pointed to by this generic ID pointer, which is something you get in Objective-C that you don't necessarily get in other languages. And you're trying to use them all together, but you don't know what they are. Because you didn't label them frac and comp. You labeled them object 1 and object 2. Well, you could stick something in there that says, ID, and it comes back and says what it is. I am a fraction. I am a complex number. And then you can figure out, oh, okay, now make this complex number, make it reference to a complex type. And then once you do that, then you can call all the complex methods on it. And then the fraction can be treated like a fraction and vice versa. So when you get that, more complicated applications where you've got lots of objects you're trying to all house together in an array of objects or something, or you're sending objects to methods and you want the method to figure out what object is this because I need to do something with this and I don't know what it is. So if you implement a protocol, you can kind of set some information. So sometimes they call that leaving cookies behind, or leaving a trail, so the object is self-identifiable. The ISA relationship's different. It's the same as other languages. We have that in Objective-C as well. The ISA means, going back to that other example, every teacher is a employee, is a person, or everybody in the same object line has the same relationship amongst themselves. Questions on protocols. Next time we're going to implement a protocol, and we're also going to do the other one. So we have two of them that are going to be in one, actually. One example that has both of them in there. Categories and protocols. Categories and protocols are very similar. I don't necessarily want to get into categories right now because I wanted to save a half hour for setting these devices up. So we'll have an easy day today. That's the last of the assignment examples. If you have started working on assignments, now is your opportunity. I'm going to reserve a half an hour here or so at the end of this. Well, I've got at least a half hour to an hour. What I'd like to do is set up devices. So hopefully you guys brought your devices in. So consider this study time / device setup / question answer session for anyone who has started to work on stuff and has discovered problems. This was the 4th class meeting, which means we have one more before we're going to consider ourselves intermediate people. So